Okay, so if you're anything like me, you like to apply what you've learned to questions with meaning and purpose and things that are kind of cool to know. And in the last video, I went over questions involving, pressure in the balloon and population of a town. All really cool things. And this is another super cool application of differential equations. Like before I before I knew this, I was super curious as to how temperature changed over time depending on its environment and surroundings. And this equation here, this law of cooling is it'll hopefully provide you some concrete evidence and intuition into how objects' temperatures change over time. So I'll just get right into it here. If we call the temperature of the object T, right, capital T, and the time lowercase t, so the rate at which the temperature will change, right, is equal to K times the difference between the two temperatures. Okay, that's a big part of this idea of law of cooling. Okay, so this T minus Ts, this is the difference between the two objects. So if we had, I don't know, let's say we had a cup of coffee, right? It was 30 degrees Celsius and the room was 10 degrees Celsius. So this T minus Ts, this would be the T of the object, or in this case, the coffee, minus the T of the surroundings. That's what that Ts means. So this would be 30 minus 10. So this quantity would be 20, right? So the bigger this is, the bigger the difference in temperature between the object and its surroundings, the bigger the rate of change of the temperature is. And that kind of makes sense, right? Because if you have an ice cube and you put it in a super warm, I don't know, cup of hot cocoa, that ice cube's temperature is going to increase pretty darn quick. But if you put an ice cube into a cup of cold water, it's going to increase at a slower rate because the difference between the ice cube and the cold water is much smaller than ice cube and a cup of hot cocoa, right? So that's kind of the main idea is the rate at which the temperature of an object changes. And it could be, a cup of coffee, it could be soda, it could be a shoe, it could be basketball, whatever it is, it's equal to some proportionality constant K times the difference between the two temperatures. Okay? So the actual temperatures themselves don't matter. What matters is the difference between them. So if two things are super hot, it doesn't matter that they're hot. The rate of change of temperature is going to be small because they're both hot. If both things are cold, similarly, this quantity here is going to be small because they're both cold, so the difference between them is not going to be very significant. Okay, so it's the difference between them that really matters. All right, and one more assumption we have to make for these questions is the room or the environment surrounding the object is big enough that the object of the temperature doesn't affect the temperature of the surroundings. So I know that's a super wordy sentence, but all I'm saying is that we have to assume Ts is constant. So if you had a cup of warm hot cocoa, right, and you put it in a really small box, the temperature of the box, right, or the surrounding, it's going to increase. It's not going to stay the same because if the surroundings are too small, right, there's not a lot of air around it. The warm nature of the hot cocoa is going to increase the overall surroundings temperature. So that's all I'm saying is that we're assuming Ts is constant for all these questions. So let's dive right into it here. For our first question, Trevor and Kevin are very thirsty after a long hike up Lindeman Lake. They put a can of Coca-Cola, which was 28 degrees C, in their bags into a creek of constant temperature 6 degrees C. After 15 minutes, the temperature of the can drops to 21 degrees C. Okay? What is an equation that can represent this scenario? Well, this is kind of a real world application, right? You're going on a hike and you want to cool off your can of soda, right? Your reward after getting to the top. So you put it in a lake and you want to know an equation to represent how the temperature of the soda will change. So if we go up to the top here, we know that the rate at which the can of soda's temperature will change is proportional to the difference between the can of soda and the lake that it's in. So instead of T minus Ts, I'm going to write D for difference. Okay, so I'm going to write dd by dt equals kd. So I'm saying the rate of change of the difference between the two in temperature is proportional, right? Proportional means there's a proportionality constant k to the difference between them at whole. All right, so similar to the last video, we can isolate for D. So if we want to isolate for D, we divide, well, the first thing we can do is if we divide D on both sides, right, we can times it by 1 over D, same thing. So 1 over D times, the D's cancel here, so we're left with K on the right, and we have 1 over D, right, times dd by dt. Okay, and if we multiply dt on both sides times dt, the dt's here will cancel, and we get 1 over d dd equals k dt. So you might be saying, well, how did you know we wanted to divide by d and then multiply by dt on both sides? The reason is because ultimately we're trying to find an equation for the difference in temperature, and the way to do that is to isolate for d. And you might say, well, why didn't we divide by k on both sides, like for this the first part of the question? And that's because if we divided by k, we would still have this dd by dt term on the left, and by dividing by d on both sides and then multiplying by dt, we can get an expression where we have 1 over d dd equals k dt. So see how there's a like 1 over d, these two variables are the same, right? We have two d's on the left. So by doing that, we can integrate both sides, right? Because the variable we're integrating with respect to on the left is the same, and that's kind of the purpose of, that's ultimately what I'm trying to say. So the integral of 1 over d dd is equal to the natural log, right, of d. It's the absolute value of d, but we can kind of ignore that for now. That's going to equal kt plus c. And this is kind of similar to the other examples we did in the previous videos. We're just using d for our variable of difference. Okay, and so if we go e to the power of the left and right side, and we kind of isolate, we'll find that the difference is going to be equal to e to the power of kt, right, plus c. Okay, and similar to the other videos, I'm gonna we don't even need to write this. We know how to derive it. So the ultimate thing that we'll end with is, let me see here. If you kind of follow the steps that we went over in the other question here, we'd get that the difference equals the initial difference times e to the power of kt. Okay, so I was kind of trying to give you some intuition into what this d meant, but in terms of the actual derivation, we already know how to do that, right? So that's what that d means, and now we can kind of plug this information in here. So what does this d here stand for? This d is the difference at the end of the situation between the temperature of the Coca-Cola and the water. Okay, so it says here after 15 minutes, right, the temperature drops to 21 degrees C. So that is going to give us some information in terms of what the D at the end is. So if it starts at 28 degrees and drops to 21, right? Let's see here. So 28 degrees C, the constant creek. Right. So if it's 21 at the end and the creek is 6 degrees, that means the difference between the two will be 15, right? 21 minus 6. Okay. So 15 equals, what's the initial difference? Well, the initial temperature of the Coca-Cola was 28, and the creek is always 6 degrees. So 28 minus 6, that's 22, times e to the power of kt, right? And we can figure out what k is by putting in, let's see here, by putting in 15, right? After 15 minutes, yeah, 15 for t. So if we divide both sides by 22, right, we get 15 over 22 equals e to the 15k. And if we wanted to solve for what k was exactly, we would take the natural log of both sides, right? Natural log of 15 over 22 equals the natural log of e to the 15k. Just do some algebra here, you'll find that k is going to be equal to 1 over 15 times the natural log of 15 over 22. So this is your exact value for k right here. Okay, that's your exact value for k. And if you wanted to find an equation for the temperature, right? An equation for the temperature, you know that T equals your initial temperature, right? Or sorry, it's actually gonna be your initial difference. Okay, it's gonna be your initial difference times e to the power of kt. Well, what is our k? It's a 15th ln 15 over 22 times t. And notice how here I said this was 15. The difference is actually it's going to be the eventual difference is 21 minus 6. So it's going to be 21 minus 6. If we add 6 on both sides, right, if we add 6 here and add 6 to negative 6, we're just left with 21 equals 22 e to the power 15k plus 6. So instead of d, I'm going to kind of transfer it into t here. All right, so the temperature, right, in this case, that's the 21 on the left. The temperature is equal to the initial difference here. So what is the initial difference? It is 22, right? Okay, it's equal to 22 e to the power of 1 over 15 ln 15 over 22 t. So you can kind of put the exponent into decimals there, but that's the exact value for what k is. Okay, so we're going to, that's how we can represent the actual equation and the rate constant. So, right, this is the rate, and this is the equation for t at any given time. Okay, now that we know that, we can kind of solve this next question a little bit easier here. So Trevor is too thirsty to wait any longer. Classic Trev. So he's drinking the Coca-Cola right away. But Kevin wants the soda to be 10 degrees Celsius. So remember in the question, it said after 15 minutes the temperature drops to 21. So this is when Trevor drinks his. But Kevin says, I don't want it to be 21. I want it to be 10 degrees Celsius. Even though I'm thirsty, I want it to be even colder. So we're going to figure out how long he has to wait. So which equation between these two are we going to use? Are we going to use the rate equation or the equation for t? And it's going to be the equation for t, right? Because we're trying to figure out how long he has to wait. That's that lowercase t. So if we figured out that t equals 22 e to the power of ln, or sorry, it was 1/15th ln, 15 over 22 t, right? And then it was, I forgot to tag on the plus 6 over here. It's my bad, so there should be a plus 6 there, right? Because I explained it over here. Instead of difference, we can just write, we can add 6 to both sides, so it's plus 6 there, right? Plus 6. Okay, so this is our general equation. And we know that Kevin wants it to be 10 degrees Celsius, so that's our t. So 10 equals 22 e to the 15th ln 15 over 22 t plus 6. And now we're going to try and solve for t, so we can subtract 6 on both sides. And this is kind of where it comes full circle. Now you'll see that 10 minus 6 is 4, and this is what d actually is. The difference between the can of soda and the temperature around it. Remember, the creek was 6 degrees Celsius. If his If he wants his can to be 10 degrees Celsius, the difference there is going to be 4. So 4 equals 22 e to the, it's a lot of writing, 15 over 22 t. So how can we solve for t here? Well, we can divide both sides by 22. Okay, so we get, that's 2 over 11. I'm going to try and leave it in exact values here, just to show you where the numbers are coming from. 15 over 22t. Okay, so if we take the natural log of both sides, we get the natural log of 2 over 11 equals 1 over 15 ln 15 over 22t. And the reason this e disappears is because we took the natural log of both sides, and the natural log of e is just 1. So remember the property where if we take the natural log, right, of e to the power of 1/15, natural log of 15 over 22t, we can bring this entire expression out to the front, and we just get this expression times the natural log of e, which is just 1. So we can kind of forget about the e there, if you were confused by that. Okay, so to kind of bring this home, how can we solve for t? Well, these things are all just multiplying by each other, so we can divide both sides by 1/15 natural log of 15 over 22, right? And I'm writing it in exact values just in case you didn't have a calculator or you were wondering where all the decimals came from. I'm writing it in fraction form. So this is the expression for what our time is going to be. So let me just figure it out here. So 1 divided by 15 times the natural log of 15 over 22. So the natural log of 2 over 11 divided by that number. So that's 66.8 minutes. So he's going to have to wait over an hour for his Coca-Cola to get to 10 degrees Celsius. Whether it's worth it is up to you to decide, but yeah, that's just kind of how Newton's law of cooling works. It's saying that the rate of change of temperature of an object, if the surroundings around it are big enough for it to be unaffected by the temperature of the object itself, is equal to the proportionality constant K times the difference between the object and the surroundings, its environment, right? So what we did was we called T minus TSD, right, to kind of make it one variable instead of two. And we can do some equation manipulation here to figure out what K is and also what T is at any given time. And once we have this equation and this constant K, we can do lots of super cool things to figure out, like this question was how long should he wait, but we could also figure out if he waits a certain amount of time, what will the temperature be, right? So instead of knowing what the temperature is, we could know what the time is and figure out what the temperature is. And yeah, that's just kind of some insight there. I hope this helped. Hope it taught you some things about thermodynamics and Newton's law of cooling. And I'll see you in my next video.